Chapter 10, Reaction Rates and Chemical Equilibrium. Section 3 is Equilibrium Constants. So we've seen that you can have an equilibrium when there's a possibility for a reaction to be reversible, when you can have reactants convert into products, but also products convert back into reactants. We can write a general equilibrium equation like so. You can see here the equation, and it's written A plus BB gives you CC plus DD, right? So the different kinds of letters are for the different parts of the equation. The uppercase letters represent the actual chemical species, right? These would be like the formulas for the compounds that we're dealing with, okay? And then the lowercase letters represent the numbers in front, the mole coefficients, okay? So this would be like A moles of compound A plus B moles of compound B plus C moles of compound C plus D moles of compound D, okay? So these are the components. A and B react to form C and D, but C and D can also react together to reform A and B. So at equilibrium, you have A and B forming C and D forming A and B, all of these together, and so you have some concentration of each of these substances, okay? And so we can denote the molar concentration by these square brackets, okay? This is a useful convention that we're going to use for the rest of the class, so anytime you see chemical formula or substance in square brackets like this, this really means the molar, right, which means capital M or moles per liter concentration of that chemical, okay? Concentration of substance, in this case it would be whatever substance is represented by X, okay? So this is the molar concentration of A, molar concentration of B, C, and molar concentration of D. At equilibrium, we know that the concentrations are all constant, okay? They're not necessarily equal. We don't want to assume that they're equal, but we can assume that they are constant, which means you can actually put all of those together and define a new constant that's a ratio of them. There's a way to derive this that's a little bit outside the scope of this course, but basically if you put the concentrations into a form like this, then you come up with a value for a constant called K that is always constant no matter what. As long as you're taking equilibrium concentrations of all of the species involved and you put them into this equation, you're always going to get the constant K. No matter what you start from, no matter how much of each you start with, at equilibrium, this ratio, this way of combining them together is always going to be equal to K. And so we call this the equilibrium constant because it's constant, okay? In this expression, you have the concentrations here, which means actually measuring the molar concentrations and coming up with a number, but then taking that number and raising it to the power of the molar coefficient. Okay, so these exponents here are the coefficients in front of the species in the chemical equation. This A is this A, this B is this B. Okay, so we're raising the concentration to the power of the coefficient. Also, we want to keep in mind that the products are always going on the top and the reactants are always going on the bottom. Okay? And so if we have more than one product or more than one reactant, then we just multiply those terms together. So this is the concentration of C raised to the power of little c multiplied by the concentration of D raised to the power of little d. Okay? So make sure you understand that this is multiplication and not addition. If you put these terms in as being added together, like I've seen some students do in the past, you'll get the wrong answer. Okay? Every chemical reaction has a unique value for K. Okay? The thing that determines K is really the difference in energy between the reactants and the products, but we're not going to worry too much about that theory for now. All we need to know is that every reaction has its own unique value for K. And the value of K can tell you something about the equilibrium mixture. Okay? Because it's the ratio of products to reactants, it can tell you whether you have more products or more reactants or about equal amounts of both. Okay? So there's a lot of information that's found in K that you can obtain from calculating K. So this formula for the equilibrium constant is a little bit confusing when you first encounter it. So the best way to learn it is to do some examples. So in this problem it says, write an equilibrium expression for the following reaction. We have 2 moles of carbon monoxide combines with 1 mole of oxygen and produces 2 moles of carbon dioxide. And we see that this is an equilibrium or a reversible reaction because it has these two-way arrows. So step one in figuring out the equilibrium expression is to make sure you have the correct equation, right? So in this case, they gave us the equation. It's not really much to it, but we have the equation here. It has the reactants, and we have the products. Step two is to begin to write the general form of the equilibrium expression. So the equilibrium expression means Kc equals some function of the concentrations of the substances involved. Okay, so the general form is that the Kc equals the concentration of the products divided by the concentration of the reactants. Okay, we often use this sort of generic form for K to remind us that the products go on top and the reactants go on bottom. It helps us to understand this as a ratio between the two. And then we just have to remember to modify it a little bit for however many products we have and whether they have exponents because they have coefficients. Okay. For now, we just need to pick out which are the products and which are the reactants. So the products are CO2, and that's it. Okay. There's a 2 in front here, but we leave that off. Okay. So sometimes I've seen students write 2 CO2 in the brackets like this. Okay. That 2 is not a part of the formula, right? The 2 in front means that you have 2 molecules of the substance with the formula CO2. So we leave out that from there, and we just have CO2. Same thing with the CO and the oxygen, right? We have 2 CO, but that just gets written as the concentration of CO, and then that gets multiplied by the concentration of oxygen. Okay, again, this is multiplication. You can leave out the dot or the cross symbol for multiplication. If you're just writing them next to each other, the implication is that you multiply them together. Okay, so just carbon dioxide on the top, and then both reactants, carbon monoxide and oxygen, are on the bottom. And then the last step, once you have everything in its right place, is just use the coefficients as powers. So here, CO has a coefficient of 2, which means CO concentration gets raised to the second power. The carbon dioxide concentration is also 2, so the carbon dioxide concentration also gets raised to the second power. Okay. This oxygen has no numeral in front, no coefficient. You could assume that it's a 1, which means you would assume that there's a 1 here. But multiplying by 1 doesn't matter, so you can ignore that. And raising something to the power of 1 doesn't matter, so you can ignore that. Okay. So this is the final answer. The equilibrium expression is the form of the equation for K. Kc equals carbon dioxide concentration squared divided by the carbon monoxide concentration squared times the oxygen concentration. So far, we've looked at pretty straightforward, simple chemical equilibrium systems where everything, all of the substances, reactants, and products were in the same state, the same physical state or state of matter. These are what are known as homogeneous equilibria. Okay? So if you have an equilibrium and all of the reactants and products are in the same physical state, meaning they're all solid, or they're all liquid, or they're all gas, or they're all aqueous, that is homogeneous. So pretty much the same sense that we mean for homogeneous mixtures, right? In a homogeneous mixture, you can't tell what the different parts are because everything's all mixed together in one continuous sort of uniform state. So the homogeneous equilibrium is the same. All of the different components are mixed together in a way that you can't really tell them apart because they all have the same phase or physical state. But you can also have an equilibrium where certain components are in one phase or one state of matter and other components are in a different state of matter. These are what's known as heterogeneous equilibrium. Again, similar to a heterogeneous mixture. Now you can see the different parts. So for instance, here we have sodium bicarbonate, which is NaHCO3. And 1 or 2 moles of this can decompose into a mole of sodium carbonate and a mole of carbon dioxide and a mole of water vapor. So this is very clearly separate states. Here there's a solid, and this is a salt-like solid. It's a white crystalline powder. And then the product is also a similar looking crystalline white powder. But the gases that are given off, CO2 and H2O, are vapors, right? They're totally in a different state. We could trap them and contain them and keep this in a closed container to have it reach equilibrium. But the gas and the solid are in different phases. So this is heterogeneous. The important thing to remember about heterogeneous equilibrium is that you only consider the concentrations for gases and solutes, meaning things in the aqueous phase. Okay? So you look for anything that has a G after it or an AQ after it. Okay, for aqueous phase. You do not consider solids or liquids. The reason is that solids and liquids, if we're thinking about the concentration of them, it's not typically how we talk about solids and liquids, but the concentration is the amount of substance in a given volume. So for a pure liquid or a pure solid, that really refers to the density. And the density is just going to be a constant. So we can take the density to be a constant and sort of fold it into the equilibrium constant and then just forget about it. Okay? So this is essentially a convention that's used, and you just have to keep in mind. You don't include solids or liquids in the expression for an equilibrium constant. Okay? Only gas phase reactants or products, or aqueous phase reactants or products. So in this case, we have two solids and two gases, and so the gases are the only thing that show up in the equilibrium expression. Okay? We could write the whole thing out, right? I could write this whole thing where I also include the concentration of Na2CO3, sodium carbonate. Those are the three products, and then I divide it by the concentration of sodium bicarbonate, NaHCO3, and I would raise that to the second power because there's a 2 here. Everything else just has a 1, so there's none of that. So I could write this whole thing out, but then I have to recognize that this is a solid, and so I get rid of it, and this is a solid, and so I get rid of this, right? Or you can think about it as getting rid of them or setting them equal to 1. Okay? And so what we're left with are the concentrations of the two gases, carbon dioxide and water vapor. Okay? In this case, by the way, water is only included because it's explicitly said that it's in the gas phase. If the water produced were in the liquid form, which it sometimes is, then you leave that out as well. So let's do an example of that. Here we have 4 moles of HCl plus 1 mole of oxygen yields 2 moles of water and 2 moles of chlorine gas. So again, to do the equilibrium expression, we need the equation. Luckily, it's just been given to us this time, so we don't need to do much about it. We can double check and make sure that it's balanced, but this one is, so we can move on. The next step is to write the general form, including all of the products and all of the reactants, but making sure to leave out any solids or liquids. Okay? So in this case, we have a gas, another gas, a liquid, and then a gas. Okay? So this liquid, water, is going to be left out of the equilibrium expression. So that means the only product I need to put is chlorine gas, Cl2, and then the reactants are HCl, hydrogen chloride, or hydrochloric acid. Well, as a gas, it's hydrogen chloride, and oxygen gas, O2. And then the last step is to include those coefficients, right? We're still leaving out water, so I ignore that. The Cl2 gets a 2 power. It gets raised to the power of 2, or squared, and HCl gets raised to the power of 4. Okay? Oxygen, again, just has a 1, so you leave it as a 1. And so this is the final expression. The only thing different here from the example we did previously is that there's a liquid here which gets left out of the equilibrium. It's important to keep in mind that we can actually measure the equilibrium constant. Once we've figured out the form of the constant from the equation, then all we need to do is run the experiment. In this case, we're dealing with the hydrogen and iodine equilibrium again. So we can just combine some hydrogen and some iodine into a container, come back a little bit later, make sure that it's reached equilibrium, and then we just measure the concentrations of the three components. We measure how much hydrogen is left, how much iodine is left, and how much hydrogen iodide has been created. Once you have those measurements, those concentrations, you put them into this equation for Kc, and you calculate your answer. Okay? In this case, if we run the experiment at 427 degrees Celsius, we get a K value of 54. Okay? So for a given temperature, the value of K is always going to be the same for a reaction. Okay? No matter what you start with, the reaction mixture at equilibrium is always going to give you the same value for K. So no matter how much hydrogen and iodine and HI you initially put into this container, you're always going to get 54. This chart further illustrates that. It shows 3 different experiments and the data obtained from them for calculating Kc for this same reaction. Hydrogen plus iodine gives you hydrogen iodide. And these were all done at the same temperature, at 427 degrees Celsius. So for each of these 3 experiments, they put a different amount of hydrogen and iodine into the flask, and they waited some time for it to reach equilibrium, and then they came back and they measured all 3 concentrations. And these 3 columns are the 3 concentrations that they measured at equilibrium. Okay? So for the first experiment, once it reached equilibrium, they found that there was 0.1 molar hydrogen gas, 0.2 molar iodine gas, and 1.04 molar hydrogen iodide gas. And so they put that into the expression, the equilibrium expression, 1.04 squared divided by 0.1 times 0.2, and they got a value of 54. The other two experiments, they started with different amounts of hydrogen and iodine, and when they came back at equilibrium, they found different amounts, right? So in this case, they had the same concentration. They were both 0.2 molar, and then the product was 1.47 molar. Either way, though, you put this into the expression and you still get 54 as your answer. Same thing for experiment 3. Now we have more hydrogen at equilibrium than iodine, and then you have 1.66 molar hydrogen iodide. And again, put these into the expression and you get 54. Okay? So this relationship between the amount of product and the amount of reactant you have at equilibrium is constant and defined by the equilibrium constant. Now we know that the equilibrium constant will have a different form depending on the chemical equation we're looking at. So at first it seems like you might have different Ks for different reactions that have different units. So for instance, in the previous example, we had units of molar squared divided by molar squared. Those cancel out, and so it gave us Kc equals 54, and there were no units. Okay, so that was sort of a fortuitous example because they canceled out. But even if it doesn't look like they cancel out, we generally just leave the units off of K. Okay, so there is a more advanced treatment of this topic where we introduce new factors that account for the concentrations. But for our purposes, it's enough to just say that K is always unitless. So no matter what units it looks like should be left over based on how you combine the different concentrations in the expression, forget about all that. All you need to know is that K is unitless. K is a pure number that has no units. Later on, when we calculate concentrations from K, the concentrations that we get will always have units of molarity, capital M, or moles per liter. Okay, so that is going to come from the conventions that we use for calculating K or for looking K up in tables in a textbook somewhere. Those will always turn out to be molar. But K itself is always unitless. So let's look at a couple of examples where we want to calculate K for a given reaction, where they gave us information about the equilibrium mixture and they want us to find K. So this problem says the decomposition of dinitrogen tetroxide, that's N2O4, forms nitrogen dioxide, that's NO2. Okay, so here we have the equation showing 1 mole of N2O4 decomposes or breaks apart into 2 moles of NO2, nitrogen dioxide. So the question is, what is the value of K at 100 degrees Celsius if a reaction mixture at equilibrium contains 0.45 molar dinitrogen tetroxide and 0.31 molar nitrogen dioxide? So if we're looking for the K, right, we want to find the value of K, which means we're going to need the equilibrium expression from the equation, but we're also going to need the concentrations for the different species at equilibrium. Okay? So lucky we're given all this. We're given the concentrations for both components of the equilibrium. We're given the balanced chemical equation. And we're going to have to find the equilibrium expression in order to connect all of these things together. So step 2 is write the equilibrium expression. We're not going to go through it piece by piece, but you can refer back to the previous examples. In this case, we just have the concentration of NO2 raised to the power of 2 divided by the concentration of N2O4. So this is the complete equilibrium expression. And then it's very simple. It's just a matter of substituting in the values that were given for those parts of the equilibrium expression. So the numerator is the concentration of NO2 raised to the second power, so that's going to be 0.31 squared. And the denominator is the concentration of N2O4 raised to the first power, and just left alone. So it's 0.45. And so when you put these together, 0.31 squared divided by 0.45, you get 0.21. So this is the value, the numerical value for the equilibrium constant Kc. And this is at 100 degrees. Here's another example using the same equilibrium reaction we've seen several times now. Hydrogen plus iodine yields 2 moles of hydrogen iodide. And so the question is, what is the value of Kc at 443 degrees Celsius if the equilibrium concentrations are as follows? And it tells you the concentration of hydrogen is 1.2 molar, the concentration of iodine is 1.2 molar, and the concentration of hydrogen iodide is 0.35 molar. So again, we have the concentrations for all of the species given in the chemical equation, and so we're going to need the equilibrium expression to relate these together. So step one is to take all this information, figure out that from what you have, in order to get the K, you're going to need the equilibrium expression. Step two then is to write the equilibrium expression. So here we have the concentration of hydrogen iodide, the product, and it's raised to the power of 2 because there's a 2 coefficient in front of it. Right, so that's that 2. For both of the reactants, there's no coefficient in front, so we don't need to worry about exponents, but it's the concentration of hydrogen multiplied by the concentration of iodine. And then we just plug in the numbers. So 0.35 is the concentration of HI that goes into the top and gets squared. And both of the reactant concentrations are 1.2, so those go in the denominator. And we end up with a value for Kc of 8.5 times 10 to the minus 2.